Been here for 7 years.
Right. Anyway, yeah, actually, I got angry at all the number, but.
Like, this is actually.
No, actually, I said, I was talking to someone. It's just to see where it would get me, didn't get me for it. Yeah, actually, and Todd said he called it and said, and somehow he got a text or some kind of message from me that said that I'm in a real bind and I need $400 worth of Amazon gift cards and I'll pay them right back. It's like, wow. I don't know, but I'm gonna go check my mailbox to see if there's some gift cards. So,
Our grad students really the target for these phishing scams. Like, we're gonna be going, like, yeah, we have no money.
yeah.
Yeah, joke's on them. We don't actually have enough money to buy a $10.
Like, we don't have pensions for them.
Okay. Definition. First off, I talked about these valuation domains. I did give them a teaser last time, and it's going to turn out that these are domains where you've got, if you pick any two non-zero elements, one of them divides the other. Seems like a really strong condition, and in a certain sense it is. Let K be a field. So what I'm going to tell you about first is what I'm going to call a valuation. A valuation that I'll call V on K. Say V. By K star, I mean the non-zero elements of K. So the valuation is defined on everything except V. Sometimes you define the valuation of V to be infinity or negative infinity, depending on the context of what you need. And gamma, totally ordered. Function B satisfies the following. Number one, the value of a product is some value. So in this sense, it's something like a logarithm, right? And two, the value of A plus B is greater than or equal to the minimum of the value of A. And quality. Yeah, the value of A is not equal to value. By the way, that last statement is not definitely only it. It's possible to have quality values A and B are the same, but sometimes yes, sometimes no. But if the values A and B are different, then you have quality. So, and I said something cryptic, I think last time about this being a measure of size, and in a certain sense it is, because what you're doing is you're assigning each element of non-zero element K an element of this totally ordered billion group. And so it's a group, so it's got the group structure on it, an additive structure, but also that means that you can compare things. And you can completely compare things. Any pair of elements in gamma, one of them is greater than the other. Popular totally ordered billion groups that you'll see valuation domains are the integers, for example, or rational numbers, real numbers under addition. Basically, this means that this converts multiplication to addition, so it's like a logarithm that way. So it's a homomorphism from the multiplicative group K star into this additive total work moving group. And it's got this thing that sort of maybe mimics, it's sort of maybe reminiscent of a triangle inequality type. Let me get the following proposition. 9. Let V be an integral domain with quotient field K. Integral domain. With quotient field.
How it really is.
Yeah, that is.
We'll name our quotient field column.
Following conditions are true. Number one, for all non-zero, give me two pair of non-zero elements, one divides the other. For all that's kind of interesting, right? For every non-zero element in the quotient field, either that element is in V or its reciprocal is in V. And sometimes no. V V is the set of X in K star such that value of X is greater than or equal to 0. Some valuation beyond that. Okay, so let's make a connection here. All right. I'm not going to go. I'm not going to do this as efficiently as possible. I'm going to do one at 2, and then I'm going to connect 3. Okay, so suppose that we have for every non-zero, for every pair of non-zero elements of V, one of them divides the other. Let's let U be a non-zero element quotient field, then U can be written as a fraction where A and B are both non-zero elements of the quotient field. Notice the denominator is non-zero by definition, and the numerator is 0 because U is not in it's not 0. B divides A, then U is in B, and if A divides B, B divides A means this fraction is actually in B, and otherwise it's reciprocal. And the other direction is almost the same. let's suppose A, B, or elements B that are not zero. A over B in A star. Since both of these are non-zero, I can form this fraction free with A over B or B over A. But in particular, A over B is A star. If A over B is in B, then B times A, and if B over A is in B times okay, so see what they want. Three. I'm all right, 3 plus 1, 2. Because I don't know what I'm gonna do yet, and 1 and 2 are equivalent, right? So I've shown 1 and 2 are equivalent, so I can do any verification, I'm good to go. So what do we have? We have the V is equal to this right here, right? It's all the elements of K star that have value greater than or equal to 0 for some valuation B. We want to show that A divided B or B divided A. Well, but UV K star, we want to show that U or U inverse is in B, right? So, notice the value of 1 is 0. This follows, of course, from the product, but let me take this way. Notice this. K star is an ability group under multiplication, right? And gamma, the image, is some other ability group. I can say ability by definition, I hope. Yeah. Okay, good. So we know that it must take the identity of K star to the identity of the data group. So B of 1 is 0. Which is so 1 of the inverse must be greater than or equal to 0. But if they're both negative, then that's a contradiction. Therefore, U or inverse. So I guess that 2 or 3 plus. Now, I want to 1 and 2 plus 3. How do we build valuation, right? So what do we have? We have these equivalent conditions. Given any A, B, and B, or A by B, B by A, we have U and K, U inverse is in B. we need to go back. Any idea? So we're gonna build a valuation, Mark, totally worth it. There are two things on my list, right? I need my total order bill. And I need, that. But this requires a little bit of kind of cleverness. Okay, yeah, actually, you're on the right track.
That doesn't seem like it gives total work.
You can actually do this. You can actually do this for any, so I'm going to do a construction. I am going to build my total order bill group first, right? You can do this construction I'm going to do for any interval domain, right? It's just that usually won't be total, it will just be a partial order bill group. I'm going to build a gamut of spots. Like gamma. A star mod units. Notice the K star is a multiplicative group of the non-zero elements of the field. The units of V, well, certainly it's not empty because V has an identity. So it's got at least that going for it, right? And in fact, I claim, forget the fact this is a valuation domain, or it has those properties 1 and 2. You can do this for any. You can take the non-zero rationals and mod out by the units of the integers, which is plus or minus 1. And what does that essentially do? When you take the non-zero rationals and the multiplication, you mod out by plus or minus 1, you're declaring the plus or minus 1 are the same thing. So it's isomorphic to the group of positive rationals in the multiplication. Right? But under the ordering, that's actually not totally ordered under the ordering that I do. It is totally ordered under the usual notion of absolute value. Here's the order. We declare. And I think, Jared, I think this was kind of what you're getting at. We're going to declare that X I am going to declare that the coset X and V is less than Y U, if and only Y over X is infinite. Notice that, for example, if this were rational numbers, if kids write the numbers, and this is units of the integers, this is not fully ordered, because the coset 2 and 3 are not common, because 2 over 3 is not an integer, 3 over 2 is not. For valuation, every pair of cosets will be common. Let's see how this works. First thing I think I've got to convince you is that this is in fact a partial order first and total order, right? Notice that A U B plus enter A U B. I check that off, right, because A over A is 1, which is in. What else do I need for a partial ordering? I need anti-symmetry, right? So suppose A U B is less than or equal to B U B. And B U B is less than or equal to A U B. This implies that A over B, B over A. B over A, and A over B. So B divides A and A divides B. Therefore, A and B are associates. Right. A divides B, B divides A. That means since we're talking in interval domain, they vary by a unit. Therefore, A and B. So I've got anti-symmetry, which I need for a partial order. And finally, I need transitivity. So if A and B, B and G is less than C, and this means that B over A and C over A over B is of course ring, so C over A to B. Therefore, A and B. By the way, notice again, I think it's always good to notice in your proofs what you use and what you don't. At this point, up to this point, I've never used anything special about the B, other than the fact it's just an ordinary old interval domain. So everything so far, I've got a partial order, right? So as a sidebar, this construction will always give you something interesting. It will give you a partial order proof. Now, I really want it to be total order because that's what I said. And so let's make sure that this is total order. And this is where I think I'm going to have to use the fact that this is valuation. So sure this is total order. So let's let well, what do I notice? Well, notice that either B divides A or A divides B in this valuation. But now I've used the fact this is valuation domain. Therefore, so one of those two has to go. So Right. I'm gonna read the last of this. I want you to, especially this one, see if you can verify this property. Again, it would depend on like these valuation. I think that defining again this way makes what the valuation should be fairly honest. Be of extra person. Let me point out that this property, let me go through this property. I'll let you guys figure this one out. Number one, Y is XY. X, Y. And I know I said plus here, but remember, this is respecting the operation of cosinus, right? So this is really the same thing. We write plus here to emphasize this is an ability group, and this is a homomorphism of ability groups. Problem is I wrote my cosets here multiplicative since they can't be this multiplicative group. But this satisfies this condition right here. See if you can get the same. Okay, any questions? Okay, here is a big, wonderful fact about valuation domains, and it is actually the beginning. The last thing that I proved for you last time was that if you have a bunch of integral closed domains, right? And remember what that means is everything in the quotient field is integral over the domains already there. You have a bunch of integral closed domains, you intersect them, it'll still be integral closed. Here's another piece to a big theorem that we'll have after a bit. 1, 2, 3. Any valuation of is integral closed. So valuation domains are always integral closed. Okay, I'm going to use that lemma from last time. It's kind of a fun application. But the evaluation domain, and of course, change. I'm going to just throw in, I will not, my proof. Of course, let me point out that, of course, alpha, if alpha is 0, then it's in B, so there's no problem there. Okay, so here's the set. The VB evaluation domain would push for K, but alpha be a non-zero element of K that's integral of B. What we want to do is show that this integral element is actually already in V. Well, if it's in V, then we're done. And if it's not, then alpha inverse is in V, right? But as alpha is in V, alpha is contained in V adjoining alpha inverse. Y'all remember that limit from last time? I may have calculated alphas, but it doesn't matter. I may have rearranged alpha and alpha inverse here, so it's the same. But alpha inverse is in V, so V alpha inverse is V, so either case. So V is in both. Okay. Any questions? So let me give you a list of some properties, by no means exhaustive, that a valuation domain enjoys. So these are kind of some of the biggies, some of the nice properties of valuation domains. There are. And we have a problem. The ideal is to be on linearly ordered. That's amazing, right? It's like a big deck of cards. They're linearly ordered. Just you want to change. Yeah, and most rings you don't expect this to happen at all. And the integers, pick your two favorite primes, 3 and 5. Neither one of these ideals contains the other. In valuation domains, it's just a stack. The zero ideal and just it's just a linear ordered stack of ideals. That's really cool. Number 2, B is quasi-local. And if you don't quite remember that terminology, what that means is B has one and only one max Y. Of course, each computer proves about that. It's a max Y deal, B has only one. Radical ideal. B. And 4. Finally, degenerate. Properties. And I think I've been mean, I gave you some examples last time, but I think we can do some more here. So I'm going to assume they're not comparable. There exists, let's say X and I, and Y and J and I. Really what this is showing is this is an I and J. If I is not contained inside of J, then there must be some X inside of J. And if J is not contained in I, then there's some Y. Let's see. One of them has survived the other. So without loss of generality, say X divides Y. So Y is XP some. Y. So into ideals. Right. Take two maxwell ideals in one and two. One of them contains the other. So whichever one is containing the other one is proper. Can't be maxwell. Anybody, does anybody know why it's true to be radical ideals or not? Does anybody remember from last semester how we characterized radical ideals? Radical characterization. There was this orange learning group, maybe back in the day, where we showed that if you intersect any family of crimes, it's a radical ideal. And converse is also true. If you had any radical ideal, it was actually any ideal that's a radical ideal, it's an intersection of other crimes. So, using that, I will go through all the detail, maybe. But I can be radical. I is the intersection I is the intersection of all prime ideals P contained. But all these P's are comparable. So the only thing missing from this is I'm going to make this following short claim. Yep. EI yeah. me write this. Suppose A, B is an I. Let's just say B is one. So, subset. Let me just say this, so- There's a subset, J of M, such that wall J and J B is not. I mean, such more than have a actually, well, so not only is the subset. I'm sorry. I completely forgot that. There we go. If, so let me work this out. So if A is contained in PI, right, because A is in PK. And on the other hand, PJ is not contained in PI. It's contained in PJ. But B is not in PJ, not in PI. And that establishes. So that is, if you have an intersection of a chain of probabilities, it's a problem. Okay, last claim is this business about any product generated by the opening principle. So, Brett, I'm going to go by induction. principal, right? The two case is the heavy lifting case, and then we're kind of there. So. Where so let me what works. So, T is equal to A1, okay, that's all we need. Right, whichever one divides the other, let's generate. And now, assume true for I equals A1, A2, and N. So we'll assume that any N generated value is principal. Let J well, this one is principal. So it's easy to show this is B one. With B is the principal generator for the first 10 elements. And this is principal. Like this. Okay. Any questions on that? Any questions? I'll go ahead, Todd. I'll see if we can start off giving you guys some examples. If you got any questions, I'll be in my office. There will be class, but my office hour is not on Friday, so if there's any difficulties, just let me give me a holler.
Particularly after your professor's gaslighting us and the thing we don't know how to do that. Because they changed the problem and once again, it's pretending like they didn't.
Hey, John.
I took a picture of
Yes, the linear order second.
when I went to do it like 5 days ago.
See?
Changed
Is that
it. Yeah.
take care of it?
Wait,
Once
let me see
again.
this. See?
Yeah.
Wait, that's what mine says. Mine
All
says
right,
K.
y'all have a good
Oh,
one.
mine says K.